my section here is control overview. The purpose of a door control is to control the sequencing of opening and closing, usually with the time delay built in. Early controls were very primitive. We've talked about that, and they basically fell into two groups. Slide door controls drive the motors in both directions. In early days, this was done with a reversing relay we talked about. Made a lot of racket, made a lot of noise. Activating the door would start with a time delay circuit, which would energize the relay in the reversing relay. A lot of times what that would do is it would charge that relay, and you have a capacitor and he's bleeding off. And as soon as he bleeds off, then the door turns around and runs the other direction. So if you gave it a short hit of an activate signal, just a real pop, you might not charge that capacitor all the way. And so your time delay would be different, and it wouldn't get a full charge and come back closed. The change in the state of the relay moves the motor leads that was in the contact from the plus side of the motor to the minus side, and does the opposite side on the other contact, effectively changing the direction of the motor. So as we've talked about, DC motors, positive and negative sides, and that's how we drive them open and close. When the time delay expires, the relay returns to its normal state, restores the control to the typical close mode when the relay is not energized. These controls were typically fitted with motor cutoff switches in both the open and close positions. It was a slide door, so as soon as he slid all the way open, we could just leave him there. It's not a swing door that's got a stored energy in a spring that we've got to keep it pinned against the full open stop. The further refinements added open and close checks, which slowed the door down. In those early stages that we were talking about earlier, we were running taps off of the transformers. So we had a 15-volt tap, or we had a 30-volt tap, and you had slide selector switches, much like in the window control today, that slowed it or slowed it down. So that was your open and close positions. The earlier controls relied on rudimentary electronic methods such as a capacitor for networks, time delays, other functions. It was your time delay, you charged it, you charged that capacitor, and hopefully you got it all the way up to full so that it could expire and drive the door the other direction. Full open speed and open check were controlled by cam actuated microswitches. Swing door controls have to maintain power to the motor when being held open. We're talking about the spring being energized. It's fully open. We're having to keep it pinned there. Once the door has been released to close, the control is basically out of the operation and turns off. In the full open position, the spring starts the closing cycle with its speed being controlled by the diode that we talked about in the it's floating around here, I don't see it, but the ohms pot, the 250 ohms pot that's floating around, and variable resistor arrangement. So at 10 degrees from fully closed, the cam actuated latch check switch trips and further breaks the closing speed, which takes that variable resistor out of the circuit. And now we're almost fully shorted on that motor. So as technology has advanced, integrated chips become available to do things like timing, amplification, and were integrated into the controls. A PAL chip, programmable array logic, was state-of-the-art at the time, but it was somewhat short of a microprocessor. So we could tell it everything to do, but it wasn't a microprocessor. It's just on the edge of being a processor. The biggest obstacle was to overcome was determining door position. Where am I at? It doesn't know if it's full open, full closed, unless it's on a switch. Swing door controls only knew where they were for a brief moment when they were tripping those switches. Slide door controls knew close cutoff, close check, and open cutoff. Simple sequencing could be obtained with existing technology and was used in the earlier slide door control. So, and you guys see these out there in the field. They're still there, all the micro switches, yes. So as the door goes open, he's out there in mid-stroke. He doesn't know where he's at. He's looking for the next switch. And so he's looking for that open check switch, and then he hits that cutoff switch. So the available solution was motor shaft driven encoders, but they required a microprocessor to interpret pulses. And so our first pulses, when we first started doing this, was the 3-pulse. Was a 3-pulse motor on, what was that, 2,100 to 1? 65 to 1 or something like that. Or anyway, it was one of our very first ones, but it had looked like a clover leaf that we put on the back of the motor, 3-pulse encoder.
Well, that was on the
6160s. It was
Industrial.
the industrials. They were 100 to 1 or 50 to 1. And I think we had some 25 to 1s too. But any case, and so it sat there on the back of the motor, and we looked at that as our pulses to drive the door open and closed. And then we started seeing where we were at. And we knew exactly where we were at going open and going closed by the pulse count. So, as processors are, they're stupid. They all know. They only know what's being fed into them. And so, by manipulating the inputs, they can do anything that they need to do by we telling them what to do. And so they read in numbers. So they must have detailed and flawless instructions. And so all of us own a cell phone, and we all get updates. And you get an update, it says, oh, okay, they found a bug. This fix iOS, da-da-da-da. Somebody discovered a bug, fixes. So they're always creating something, and whenever they create something, they create a bug somewhere else. And so, but their memory has to be absolutely flawless in order to perform. So they make decisions at the speed of light. So the next guy we're going to meet microprocessor here. So Mr. Microprocessor here is getting all of his orders from headquarters, and so he's reading all that script right there. And he's got his run fast motors, and he cannot see the outside world only through the switches that are coming into him. So he's sitting in this control room, and that's what he does. He sees that light come on, this light come on, and he reacts and turns the motor on or off or runs slow or whatever. And that's what he's doing, all at the speed of light. So he's supposed to be able to hustle a little bit. This is our current 3150 microprocessor Zilog chip. It's an 82-pin chip, and this is what you'll see in the 3150.
about the size of a quarter.
Yeah, he's about the size of a quarter. He is what we call flashable, and where our other chips were not flashable. So if we wanted to update you or do something else, we would send a new chip to you. This guy, we can flash, and but what we ask you to do is send the control back to us. We reflash it, send it back out.
How long does that process take, like turnaround time?
It's quick. I mean, we can flash it immediately.
But we've got a pool, so if you have one that you're gonna upgrade, you call us, we send you, what is OSUG, which is an outside software upgrade. And then when we get yours back, then we credit, so it's whatever the shipping time is. We'd send you, you won't be getting the same control back, you'll get a control with updated software. And you could have it as quick as you could get a new control, right, Jeff?
Yep. Now on the current 3150s, we are up to version 3.15, and we believe we're going to be good for a long time with that.
1503.
What did I say?
315 fuse.
1503.
There you go.
That's what I meant to say. 1503. Sorry. We believe we're going to be there for a long time. So any control version prior to that, especially up through version 2, is susceptible to.
I'll be talking about that.
Oh, okay,
at the start
sorry.
of the 3150. I'm not. You can
Okay.
talk about it if you want to. But
No. Go ahead. That's fine. I
So-
don't even know what version it is.
So this is the 2150. Everybody's very common with the 2150. There's many versions of software out there in it. It has a 40 pin. The latest, greatest version is version 11.02.
.02.
And I think I have some other pictures in here, but he does have a north-south pole on him. And we can't see it in this photograph, but this end is the North Pole, and there's a little mouse hole, and in the socket base there's also a little mouse hole that these line up in. And so whenever you're looking at them to replace them, they are, oh yeah, you can see it. It's way up there on the end. You see that little indentation right there? That,
You've got a better picture.
I may have a better picture of it, but that right there is the north end of the, what I would call the north end of the switch. And the socket also has that same spot on its chip base, on the socket base, and it's right there. There it is right there. So there's a better picture of it right there. So this is what the EEPROM looks like inside. This is a close-up picture over here on the right, and this is a picture of him on the inside right here, and all the little tiny wires that are soldered in it. And then there's the chip base right there, and you can see how he socketed in all along there.
Every one of those little wires like that one will lead to one of these pins.
So the data sheet and the output of this, of the socket, of the chip, is, this is just a standard description of where everything is going. And so
You gotta have power for the chip, and it comes in on one and, the ground. And then you're gonna have all your different inputs and outputs, and, the reset button on the control will be tied to that. And when he writes a program, he'll be, directing information to the inputs and outputs. But if you looked at the data sheet for that, chip, it'd probably be 300 pages long.
When you flash these, is there like a USB port on the controller, somewhere on the PCB?
No, on this one, we have to burn the chip with a programmer. I have one in my office, and we've got one in production. But the 3150 and past is gonna have a little port that where you program it.
yeah, it's got a plug that's on it, and I'm not sure if it's FireWire, but whenever we plug into it, and we have our laptop, we plug into that, and that's how we update it. So the coding, the binary coding, is zeros and ones for all the information. So all the, like an input, such as a beam, can only be in one state. It's either off or on. Horton controls have 5 volts present for their inputs. And so Jim talked about that earlier as all of the inputs that are coming in, all the voltage that's coming in. On the 2150, this 5 volts, whenever you look at it with a meter, if you're looking at it over on the auto lock or reading for the software or anything else, when you look at it, it's 4.9 volts. It is regulated. It's one of the only places on the whole board that it has actually regulated voltage. The circuit's designed so that it's closed. If voltage drops to 0, the processor can detect that and change the states. The outputs frequently require additional circuits or components to deliver higher current to the output devices, such as your motion detectors and auto locks and things like that. So your auto lock out there, if you had your auto lock out there, it's got a 5-volt switch that turns it off and on. That's controlling the 24-volt port off of the 2150. And so we look at that 5 volts to drive the switch back and forth so we know where that lock is at. And then this is the auto lock setup and functions for the 3150. It is, as Jim said earlier, if you got a good handle on the 2150, then you're already way ahead on the 3150. The 3150 is designed by the same guy that did the 2150. The software is written by the same guy that did the 2150. So in thinking of the same way as the 2150, that 3150 is going to run very, very similar to it. Is that pretty well said, Jim? And this is the last slide that I have here. So this is a code out of the 6610 that that the software writer Donnie has written, and there's, you know, everybody's all here's watchdog timer and stuff like that. That's all built into this, and so you've got some dip switches. This is just basically how he's able to read and disable sensors, read the status of the sensors.
That part of the program is defining how the control decides whether it's a swing door,
A slide door.
6610 or a slider, true or false. And so if dip switch S16 is on, then it's going to be a swing. If it's off, it's going to be a slide. And we just did that to show you, you know, how they write the program, and you know, I'm not a programmer, but that's basically how it decides how to react to an input.